طيب inshallah today we are going to have an active class.
You post in LinkedIn, Doctor?
لا أول كابل. So inshallah we are going active today, Shabab. This is the lesson plan. So where is group 1? Group 1. Group 2, Shabab?
Yes.
Group 2. 3. Group 4. So please just stay in group close to each other. Group 5. So inshallah today we are going active. Well, inshallah group 3 they can just come in sequence here and just introduce us what they have in this class. Inshallah it will be a kind of 20-25 minutes. Then inshallah we'll be moving to, it should be including discussion because we have video shows here, Shabab. And then we can discuss it together if you have any question, and then we can move to the last part, which is the group activity. Please go ahead.
Hello everyone, we are group 3 and today we are continuing with chapter 4, focusing now on the turbine, which is a crucial component of the gas turbine engine. The main function of the turbine is to extract kinetic energy from high temperature, high speed gases existing in the combustion chamber, and then convert this kinetic energy into a shaft horsepower to drive the compressors and other engine accessories. One key point to note here is that about 3/4 of the energy that is produced from the combustion process is needed to drive the compressor, and this shows how essential the turbine is. Now let us move to the structure of the turbine.
What is so? What do you expect the efficiency in this case, Shabab, for a gas turbine engine? Is it high or low? It should be low because we have a compressor. It's taking a kind of most of the energy produced by the turbine. That means the net workout should be low in this case. This is one of the main drawbacks of the gas turbine.
And now let's move to the structure of the turbine. It consists of an axial flow turbine that has two parts. The first part is the turbine wheel or rotors, and this rotates the airflow and extracts energy from it. And the other part is the stators, which direct the airflow efficiently to the rotating blades. And modern engines now uses multi-stage turbine, which means that it will use multiple sets of rotors and stators that work together to extract the energy from the gas. And the turbine has the two parts: the high pressure turbine, which drives the high pressure compressor, and the low pressure turbine, which drives the low pressure compressor and turbofan, which drives the fan as well. And now I leave you with Haytham to complete with that.
So why we use a Shabab dual spool turbine and compressor component? So please interact and ask him. Why we do that?
I have a question.
Yeah.
Some engines like the Rolls-Royce, they have 3 shafts. They also have the middle MPT, it's called. Is that why is that? What's the point of having the MPT? If you have high pressure turbine and low pressure turbine, what do you have in mid turbine?
You have also a kind of mid turbine.
Yeah, it's called MPT, I think.
This is, I don't think it is mid turbine. They use a kind of reducing gear, as a matter of fact.
It's 3 shafts, right? High, low. Also, in the Rolls-Royce and the Airbus 330, they use also something called the middle shaft.
Middle shaft, this is maybe something for maybe startup or some other accessories to drive some other accessories, but it cannot be a shaft for, because we cannot have a kind of 3-stage turbine, 3-stage compressor. It should be a kind of accessories shaft. Because we will see, inshallah, Shabab, some of those kind of accessories, we have a kind of air turbine to act as an engine starter in this situation. So maybe shaft like this.
Like from the bleed, air bleed.
Yes, air bleeding. Yeah. The idea here, Shabab, is that high pressure compressor should be driven by high pressure turbine to spin at high speed. And then we can have the low pressure compressor driven by the low pressure turbine and the fan as well spinning at lower speed. And in some situations, Shabab, we have to have a gear to reduce the shaft from the low pressure compressor, low pressure turbine, to have a reduction gear to drive the fan, because fan has to be driven at even lower speed to draw more air and to consume less power. Please go ahead.
Okay, so there's two basic types of axial turbines, which is the impulse turbine and the reaction turbine. So let's begin with the impulse turbine. So the stated rule here is for accelerate the flow by increasing its velocity and decreasing significantly the pressure before it reaches to the rotor plate. And the rotor plate will take advantage of the high velocity flow by extracting its energy and because of its extraction of its energy, the velocity will reduce. So the output velocity of the rotors will be much less than the inlet velocity, and the pressure will remain constant in impulse turbine. The second kind, which is the reaction turbine, it's kind the same process but in different way. So the rotors here will accelerate the flow by reducing the pressure and increase the velocity, but as not much amount as the impulse turbine do. So its main function here is to guide the flow at a certain angle to be matched with the rotor angle. And the rotors will extract the energy by decreasing the pressure and the velocity. And here the reaction turbine experience some variation in pressure, which is different as the impulse turbine. So the jet engines use a combination of both impulse and reaction turbines. And if the jet engine is equipped with a dual compressor, the turbine should be a multi-stages to power the compressor stages efficiently. So when we design a turbine, we should be focused on the shaft rotational speed, gas flow rate, and the inlet and outlet temperature, because the rotor's blade shouldn't be affected by the high temperature that's coming from the compressor, and to not affect the blade material, this depends only on the material that we use for the turbine, and the inlet and outlet pressure, exhaust velocity, and we should make sure that the turbine generate amount that we need of the power to rotate the shaft and to generate the power for the compressor. Now also we will continue in the turbine types with my colleague Abdurrahman.
So Shabab here, so look at the moving blades here for impulse and reaction turbine. Moving blade in the impulse turbine, it takes the shape of bucket, Shabab, so it is symmetric. Is it? Look at it. It is symmetric. Where the flow hits? It hits at the middle almost. Is it? So it doesn't have a contact with the surface of the blade itself. So the idea here is to do what, Shabab? Impulse. Just a hit. The flow will be hitting and then leaving. So that's why if you look here, Shabab, we don't have expansion. As a matter of fact, the pressure is what? Fixed in the moving blade. But in the fixed blade takes the shape of nozzle. So the velocity would increase and the pressure would decrease. If the pressure is constant in the moving blade, why the velocity is reducing?
Because of the impulse.
Because of the impulse, that's okay. In this case, Shabab, the flow will hit. So the kinetic energy will be converted to what? Mechanical energy. So now the speed of the flow will be, reflected flow will be reduced. But on the other side, let's look at the reaction turbine. Look at the blades, moving blades. Are they symmetric? No, they are aerofoil shaped. That means we should have in this case what, Shabab? Some reaction with the flow. The flow in this case will be going between each two blades. And the area between each two blades is taking the shape of what? Nozzle. So in this case the pressure will be what? Reduced. It is not just hitting a Shabab in this case. It will hit, it's okay to drive the shaft. But it will go through also what, Shabab? The surface between the two blades. So now the flow, we have flow over the surface. And the flow, the surface itself, it takes the shape of nozzle. So now we'll hit to drive the shaft, and also the flow will be accelerated between the blades. The velocity would increase and the pressure would decrease. If I have here the pressure is decreasing. Why the velocity is not increasing? as we have flow between the moving blades?
Impact also.
Because the velocity kinetic energy is converted to what, شباب? Mechanical shaft bar. It's okay. It should increase. It's okay. But if the shaft is not rotating, shaft is rotating. So in this case, the kinetic energy is directly having some impulse in the blade, and it will drive the shaft. Type in jet engine, what kind of form should we have?
Both.
It should have a combination between both of these. Okay, we need to hit, and we need to have reaction also. Yeah.
As my friend Haytham and Doctor explained, there are key differences between both of them, being that the impact turbine gets its energy from kinetic energy, and the reaction turbine gets from pressure and kinetic energy, and also that the blades, as the doctor says, symmetric in the impact and not symmetric, has an airfoil shape in the reaction turbine. We to not bore you with this table, because I want to open something here.
Okay.
To not bore you with this table, we brought a video that will show you the working of both turbines. Here. This is the working of both turbines here. You can see, being the up one being the rotation, the reaction turbine, and the impact turbine will be down. But if you want one example of the reaction turbine, and is the what they call it, the Francis turbine. The Francis turbine is a key example of reaction turbine, and here Francis turbine working in the field. You can see here the flow is going inside the turbine here and go through the duct, moving, then going in this direction. After that, it's rotating and going in axial direction downward. And now I leave you with Ibrahim to explain nozzles.
Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you, Rahman. Good morning, everybody. My name is Ibrahim. I'm going to explain to you the exhaust nozzles. It's actually pretty basic. You understand just by following. So, the main purpose of the nozzles is to increase the velocity after the engine. The nozzles are the last part, usually are the last part in an engine, and they make sure that the hot air escapes with higher velocity to produce higher thrust. So we said that its velocity is high. Then there must be some compensation. So what do you think happens to the pressure when we increase the velocity in here? Yeah, pressure decreases, and that's known as the expansion process. So to have a high thrust, we must have a high kinetic energy at the exit, which will lead also to a faster leaving of the air, the hot air. And I mentioned before that it's also an expansion process where pressure decreases at the end of the nozzle. There are two types of nozzles. We have the convergent nozzle, we have the convergent divergent nozzle. The convergent nozzle is pretty basic. You have just a narrowing at the end. And the convergent divergent nozzle is a bit more complex. We're going to talk about in the next slide.
So Shabab, the idea here, which one to use?
Yeah,
if I have low pressure ratio, or high pressure ratio.
Ratio. It's basically the pressure ratio between the last point of the turbine and the hot air leaving. So the air outside. So if you take the ratio between these two, you find it to be less than 2, then you're going to use the simple convergent nozzle. If it was more, you're going to use the convergent divergent nozzle. And usually the low nozzle pressure ratio are existing in subsonic aircrafts, where if it was more than 2, you're going to use it properly with the convergent divergent for supersonic aircraft. As I said before, like the convergent nozzle uses the aircraft with the subsonic uses a convergent nozzle when it's less than 2, and in here, if the supersonic engine has an afterburner, you're gonna change the geometry to incorporate the aerodynamic features and have better airflow. Yeah, that's about it. It's pretty easy. You can understand it. If you have any questions, please ask. Okay,
So in a convergent divergent nozzle, should we have the throat to exit area variable? Is it?
yes, if I can go to the slide before, you can see the shape of the convergent divergence. It's actually converges and then diverges again. Because this is the pressure difference outside and in here after the turbine is going to be pretty high, so you need to change the geometry to incorporate the airflow.
You have to match the conditions here, Ishwa, because usually if we have a convergent divergent nozzle, most probably I should have afterburner. And afterburner is not on all the way. When it works, when I need to improve, increase the thrust, do maneuvering, do whatever.
The afterburner is like a booster for the...
Yes, I will be speaking about this, but in this situation we need to change the area. As we said, the operation should be all the way under what, Ashbab? The design. You see the variation of back pressure with nozzle operation, so we have to have all the way the nozzle working under the design condition. Okay, but what will happen if the back pressure is changed, if the supply pressure is changed, burning more fuel and all of this stuff? That means the design condition will be changed. So I can control the design condition by controlling what? The area ratio. Exit area to throat area to achieve all the way that the nozzle is working under the exit design condition.
Yeah, you can imagine like the afterburner is like a turbo in a car or to increase the speed momentarily.
Yes. Okay.
Okay, thank you guys. I'll leave you with Bara now to explain the slide.
Okay, now I'm going to talk about thrust augmentation. Thrust augmentation is like a boost for thrust for a short period of time. We don't use it all the time because it has drawbacks. We have two methods for thrust augmentation. One is water injection and the other is the afterburner. The first one for water injection, how do we boost the thrust from water injection? Doing is injecting water in the pressure, in the compressor chamber. By injecting water in the compressor chamber, we increase the flow rate inside the compression chamber, and we increase the flow rate, and by doing that we increase also the pressure inside the compression chamber. So when it goes to the combustion, we will have more thrust generated. We can also inject the water inside the combustion chamber, but it consumes a lot of water because it's very hot. And injecting water inside the combustion chamber can give us more than 50% thrust generated during takeoff. And the other method is using afterburner.
But here, Shabab, when do we need thrust augmentation? Usually at what?
During takeoff.
During takeoff. In this case, we may have water injection. This is very common, especially in hot day, Shabab. What does it mean hot day?
The flow rate is less.
Because the temperature is what? Is high. So the mass flow rate of air is low. So I need to increase the mass flow rate. Because increasing the mass flow rate, of course, I would increase the thrust. Thrust is M dot multiplied by the change in the flow momentum. Type injecting the water, we have two places where we can do this injection. Either at the inlet of the compressor or at the inlet of the combustion chamber. We said the one is better is what? At the inlet of the compressor. Why is that?
Because we need more water in the combustion chamber.
Of course, so we'll need more water in the combustion chamber because we are injecting at high temperature. So the water would flash and I would inject more water. But what will happen if I inject at the inlet of the compressor, Shabab? So in this case, I'm injecting the water, and also this will be what? Compressed in the compressor. What does it mean compressed? Density will be what? Will be even increase more. So that means the mass flow rate will also increase more in this case. That means in this case it is more effective to inject where, Shabab? At the inlet of the compressor, comparing to the combustion chamber. The other way is the afterburner. Please go ahead.
The afterburner is usually after the turbine and previous to the exhaust nozzle. How afterburner works? After the combustion chamber, the generated air mixture is rich with air, so we can do an extra burning process. And for the jet engine, there is also a bypass ratio. So there is also a mixture of air and the bypass. So it can all be mixed in the area between the combustion chamber and the nozzle, and can be injected with fuel and then ignited. So we can generate more thrust. But the problem with this method, it's use a lot of fuel. So it's very, it has a high specific fuel consumption. So we only do it during takeoff or high speed maneuvers. So we use it only for a short period of time.
And this is limited maybe to the military aircraft here in this case, Shabab. So usually we don't use afterburner in civil aviation aircraft because the fuel consumption will be high. That means the price of your ticket will be high in this case. Also, Shabab, here when I usually this, please get back. This already is afterburner. It's a flowing constant area duct, and we have a limiting design parameter for the combustion chamber to have the pressure. What, Shabab? Pressure has to be constant. It's okay. So that means if I'm injecting fuel and burning, what I'm doing here is what, Shabab? Raising what? Temperature. Raising the temperature will result in raising what, Shabab? The kinetic energy, and then we can generate more thrust from the propulsion nozzle in this case. So the idea, I'm not raising the pressure anymore. I'm just raising the temperature to increase the kinetic energy of the gas. Okay.
Dr. Just raising the question about the water injection. What is the science about inserting water to a mass flow to increase the thrust?
You mean the amount of water?
Yes, what is the science of adding water? Exactly, why water?
Let's move to the next slide. I will give you a clear answer about this in the first line here. You can see the amount of water injected for a given example, G57 turbojet engine. You can see it here. So please go ahead and explain this.
Now we have two examples for two turbojet engines. One is the process using the water injection, and as you can see the values, it carries a 1,500 pound of water, and it can only be used for a 90-second duration for only a short period of times.
This is used in what engine, Shabab? In J57 turbojet engine, which is used in B52. B52, Shabab, this is a bomber aircraft. It's okay. And we have KC-135, also another kind of aircraft. It is used, and they use thrust augmentation, of course, using water injection. You can see the amount of water, 500 pound, which is a kind of 250 or 260 kilogram for 90 seconds. They inject it to improve the thrust.
So you think it's in the compressor here or in the combustion chamber?
Of course, it will be injected most probably at the inlet of the compressor. Injection in the combustion chamber, this is a kind of very rare.
And for the second aircraft is G79 using the afterburner. As you can see, for the thrust generated using the afterburner is 18,000. This is with the afterburner. And the fuel consumption is approximately 2
pound mass per hour, Shabab, per each pound force. We consume almost a kind of 2 pound mass per hour. But look here, compare it, Shabab, without afterburner. Of course, the thrust is reduced.
More than the
But look at the fuel consumption. 0.8, less than half. Okay, you can imagine the amount of fuel consumed in this case.
Doctor, it's the methods of thrust augmentation. Is it mainly used for military aircraft only? There is no any civil or any other usage of it?
Most probably we don't need in civil aviation aircraft. Usually it is in some situation when you need to just take off at very short period of time. Maybe also in aircraft on the aircraft carrier in seas and all of this stuff. Then in this situation we need to take off in a very short period of time, so we do whatever technique in this case to increase the thrust. But usually other than this we don't need it, because it will add, Shabab, in civil aviation. If I have a kind of 500 kilogram of water I have to inject, this is additional weight as a matter of fact. Okay? Yeah, go. Do you have voice?
Please sort that.
Mute.
Indifferent.
are the actuating rings, the VIGBs. Then the first stage of the compressor.
What is this?
Sorry, don't move.
This is what?
The actuating ring.
Yes, this is the component of the engine.
Stator ring.
Yeah.
Second stage of the compressor. Second stage stators. Three. And down the
So
line,
stator
four.
plate plus followed by moving blade. The stator moving. Each row
Stators
is a stage.
are not variable.
So the plates of the compressor يا شباب are very thin. You can see.
There, each stage compressing by about 1.1 to 1 ratio.
Decreases the size as it goes.
The outlet guide vanes, and they direct the air straight into the diffuser, mid-frame diffuser, which contains the fuel nozzles. These are liquid fuel nozzles. They inject fuel directly into the combustor cans. Let's go back a bit. This is the mixing air holes for cooling air to mix with the flames. These are the interconnectors for the ears, for the crossfire tubes.
What is the function of the interconnector يا شباب here? Please stop. Interconnector is doing what?
Crossfire tube.
Connecting the cans.
Distributing the flame.
Connecting
Yes.
the cans to each other and
So Muhammad,
Yes, distributing the flame for all the cans.
while the ignition, and also keep the pressure what?
constant.
Constant.
Constant. Yeah. Okay.
They allow the flame to travel between the combustors that have ignited plugs and the other ones. Out of 10 combustors, only 2 of them have spark plugs or ignited plugs.
Yeah.
So the interconnectors is how the fire gets all the way around.
See يا شباب the liner, and we have the opening to have the air, secondary air should be coming in to do what يا شباب? To do the cooling, exactly.
It stays there.
Then we can move, you see here.
This is the transition duct, which we've also seen before. Turns the cylindrical outlet of the 10 combustors into an annular ring of hot gases. This is the nozzle.
Yeah.
This is the gas.
So we can, yeah, those are يا شباب, can you fix it here? So you see يا شباب the fixed, the first row fixed lid, those are what? The fixed blade takes the shape of nozzle, so the flow will be going between the plates, leaving the combustion chamber, okay? And then it will be accelerated at high speed. Then the moving blade under the finger of this guy exactly, they are on the opposite side. So the flow leaving the fixed blade will be hitting the moving blade. Then the shaft will start to rotate. And then the flow leaving the moving blade will go to the next fixed blade to be accelerated. And then to hit the next moving blade. Here we are cutting and we are removing here the fixed blade. Between each of 2 moving blade, you will find the fixed blade are just removed here to just show you the section. Yeah. Okay. So can you just go a bit faster with this video?
The turbine, causing it to turn. That sound you hear is dirt trapped in the cases hitting the ends of the compressor blade.
So why it is musical يا شباب? Can generate music here. Gas turbine is very nice, huh? So this one here يا شباب, why it is musical when you just hit it? Because its thickness is what? Is very small in the compressor. Okay, but if you move to the turbine, can you move the video, Murat? No, just move. Yeah, stop it here. Stop here. So this is the case of turbine. Can see the blade is what? Thicker, and we should have cooling in the blade, inside the blade, at the blade base itself. We have to apply cooling in this case because it is working. Turbine is working under what? High temperature, but compressor is working at low temperature. I don't need to have higher thickness. Also here, the blade being hit, the flow is hit from fixed blade to the moving blade. It has to be able to sustain this, and it is connected to the shaft to rotate the shaft. So can we go with this video? You can look at the remaining part of it, and then if you have any question, you can raise it through the blackboard. So can we move to the next video where we can have engine starting?
Gear pins are checked counterboard over at 3 seconds, so the receiving checklist is completed, sir. All right. 45 going. All right. Engine single stage, 1 row of light. Then, OCDO goes
So the basic operation of turbine engine we know already.
less than 10. Passing in spins the turbine, that drives the shaft, connects it to the fan, compressor blade.
So how we start the engine here يا شباب?
And then after
Using the APU, it
We have,
leads to
I
the
think we
engine.
have a pressurized
To start this engine we have to have the shaft what يا شباب?
rotating.
Rotating. طيب to rotate the shaft what should we do?
We put pressurized air inside the combustion chamber.
شروط what يا شباب? We have to use air fan. So we have to come up with pressurized air, then it will drive the air fan. Air fan is just a fan. The flow will just turbine. We call it air turbine. Will hit the blade of the turbine will rotate. Okay, if the air is pressurized. When it rotates, it will start rotating what يا شباب? The shaft. To start the ignition system, we have to approach a velocity, a speed, running speed, a kind of almost 12% of the total or the full operating load rotational speed of the shaft, which is a kind of high pressure turbine, maybe spinning at 100,000 RPM as a matter of fact. Okay, from 60 maybe to 100,000 RPM. Okay, type to reach this speed we can use the air fan. Okay, the air turbine we can say. And then the fuel to start to be injected in the combustion chamber, it has to be running at 25% almost of its rated speed. Okay, then we have to generate this speed using the pressurized air that can run the air turbine. But from where يا شباب we can get this air? Pressurized air. Can we move on?
The APU.
You have
It's auxiliary, the auxiliary power unit. You can just move, just show us the auxiliary power unit. Just move.
not so.
Just to get back maybe slowly to just show the auxiliary power unit where it is located.
The back of there.
In the back of the aircraft. Just move the bar until we have this scene.
Spark plug like igniters that initially light the fuel on this motor. So instead, you take pressurized air and
يعني in a small size aircraft يا شباب we use what?
also then
Battery or something. It can run if it is propeller or something. But in case of heavy duty aircraft we have to have pressurized air through the air fan. Can we move it a bit? Just to show the location, yes, get back to show the location where the auxiliary power unit in the aircraft, just a bit behind. Yes, here, yes. So here you can see this is the auxiliary power unit at the tail part of the aircraft, where it is there, but most frequently it may not be working, okay? So you don't imagine it is working all the way and it is available. So in this situation, if the air turbine, if the auxiliary power unit is not available, so what should we use, Shabab?
electrical power.
Electrical power.
Or if you have another engine as well operating.
Can you run the video here, Shabab? Have you seen it in the airport? You should have seen it in the airport. You just move it a bit. Exactly, hover cart, Shabab. So hover cart can be used in this case. You can see, just move it a bit, the video. Yes, you can see it, Shabab, here. This apply, we have a compressor that can supply compressed air to the air turbine, and then air turbine can drive to start the engine. Once we start one engine here, Shabab, we can take compressed air from any bleed air, we call it bleeding air, take it from any stage of the compressor, and then we can move the compressed air to drive the air turbine to drive the other engine in this case. Because usually we have two engines, okay, in most of the cases, okay. You can look here, Shabab, how the flow is going. Either air auxiliary power unit or hovercraft. Which one, anyone can be used, and then we can move. Okay.
One's ready to start, like this. Okay, now to start engine number one.
Yeah, that's it's okay.
Which engine usually starts first? The left one or the first one?
Allah, it can be any of them. But I think in this video they said the right engine. They call it not right and left. They call it 1 and 2.
1 and 2, yes.
1 and 2. Okay. طيب. Please go ahead, Shabab.
Now I'm
Thank you, Malak. So after knowing all the needed parts for all the used parts for the jet engine,
we need to have a convention or the numbering system to analyze and document all the analysis of the jet engine. The standard used is this is an industry-based standard, which is Aerospace Recommended Practice ARB 755A. We used it and we used it throughout this textbook. As can be seen here, the inlet section is numbered from 0 to 2. Then we have the compressor from 2 to 3, and then we have the combustion from 3 to 4, and then we have the turbine from 4 to 5, and finally we have the nozzle from 5 to 9. And also to differentiate between the low pressure compressor and high pressure compressor, we have this section to indicate the difference between them, and it's the same for the turbine. If we are using an afterburner and a converted diverted nozzle, we can see that here the section 6 and 7, 8, 9 start to appear contrary to the previous configuration, indicating the afterburner section and the inlet of the converted diverted nozzle and its throat and also its outlet. Keeping this convention in mind, we can move toward the braking cycle.
So يا شباب, here the numbering here is standard. So if I told you the pressure B3, you know B3 is what? The pressure at the outlet from where? Compressor and the inlet to the combustion chamber. And this will be the way. If I told you pressure, let's say B5, that means the exit of the turbine. B9, that is the exit of the nozzle. In case if I have convergent divergent nozzle, if I told you the pressure B8, this is the pressure at the throat, should be critical. B7, that is the inlet of the nozzle. Okay. 6, this is the inlet of the afterburner, and so on, ya shabab. If I told you 2.5, that means I have dual compressor. 2.5 is the exit from the low pressure compressor and the inlet to the high pressure compressor. And likewise, we have the turbine. Yeah.
Moving on toward the braking cycle, which is a model used in thermodynamics for an ideal gas turbine power cycle. It works under the assumption that we have chemically perfect air, and also we have fixed mass flow rate throughout all the different sections. We can use the numbering system here also. So the first phase we have is 2 to 3, which is the isentropic compression, which indicates the compressor. And then we have the constant pressure heat addition, which indicates the combustion phase from 3 to 4, which is also a constant pressure. And then we have from 4 to 9, indicating the expansion, which combines both the turbine and also the nozzle. And finally, we have the constant pressure heat rejection, which is the air exhausting the jet engine. With this, we concluded our lecture, and now we are moving toward the class activity with Dr. Mehta. Thank you.
Yeah. So Shabab here, so this is a kind of idealized cycle. I have here the cycle here, Shabab, is what? Is a closed cycle, not open cycle. Yani, I'm just using here air, circulating it. Instead of combustion chamber, I'm adding heat. Instead of having heat rejection out of the nozzle, the gas are left to the atmosphere. And then we have to take new fresh charge from air and fuel. In this case, I'm just circulating it, and then instead of heat rejection, I have instead of rejecting the exhaust gas into the atmosphere, I'm rejecting or cooling down the circulating air. So I'm just simplifying here, Shabab, by considering the closed cycle, Brighton cycle, which represents the operation of the gas turbine. Not only the gas turbine. Look at section from 4 to 9. This is expansion where, Shabab? It should be in where? In the turbine. Do we have other expansion? Where? In the nozzle. So 4 to 9 is the expansion. So we are representing the whole jet engine in this situation. Let's move to the next part, which is the part that you have to go in group activity. We need to prove the thermal efficiency of this Brighton cycle. So please go ahead, just have yourself in groups and try to finalize it. Say this is the thermal efficiency here, Shabab. We need to prove that the thermal efficiency is equal to 1 minus 1 over the pressure ratio. Of course, it will be off, and then you can do it yourself. Yes. Yes.
Can you go back to the numbering and the parts?
Yes.
I checked again the information because at Trent Saudi they have Trent engine. It has also intermediate, it's called intermediate, not middle. I said middle. Intermediate pressure turbine and intermediate pressure compressor, IPC and IPT. So where is it number in here? It's not number.
Usually, as I told you, this is the common standard. We have to have D1. Okay, we have to have dual spool. That means we have two spool
Yeah,
engine.
this is most engines. But
This
like,
is-
this engine 10700.
I told you, maybe something like this. It may be for auxiliary shaft. It can be connected, as a matter of fact, to other auxiliary system. Like where we have the air fan, we have some other shaft that can be extracted to do whatever mechanical power in this situation. But it cannot, as a matter of fact, part of this standard numbering.
So it's not in the standard.
It's not in this part. Yeah, you're right. Okay, Shabab, please go ahead. Alex, so what?
Yeah, it was.
Can you just wrap up on this?
Yeah, it was an interesting class because we have seen multiple sources like videos and like some illustrations and other than the normal slides, some of the illustrations. That's
Yeah. Yeah, so it was interesting in a way. Yeah, okay, sure.
And
So-
the practical aspect actually here, it's involved, as we can see, the real engine, not only theoretical illustrations. It wasn't,
Yeah. So what do you think about active class?
yeah, it's really good. Yeah, it's helping.
Yeah.
I'd like to add some things. I used to know that there is an afterburner, but in this class we learned that there is also a water injection,
Yeah.
which is a good knowledge.
Okay. So thank you, Shabab. So what do you think, Shabab, about the class?
Actually, it was a really effective class, as we expected.
We get the opportunity to know how the compressor works and the details of the blades and the science behind that. And we, of course, we can now imagine how this turbine and gas turbine are working to derive the thrust that we are gaining.
So how do you think, Shabab, about the active learning module? Is it interesting to have something from your side?
Until now, outside from and the slides and so on, there's like interaction between us as a team and the other students and the questions and videos media that can elaborate and illustrate the point that we want.
Yeah.
So I think it's 100% yeah, really efficient way.
Thank you, Shabab.